Welcome back. We have discussed ideal systems at length during our discussion on statistical thermodynamics. Most of the expressions which we have derived belong to ideal system, ideal gases. But we know that even if we first talk about the gases, all the gases are not perfect gases or ideal gases. We may say that the ideality or perfection is approached under certain conditions. For example, when we talk about the gases, when the pressure is very low, the gases may start behaving ideally. And when the system is not ideal, then there have to be some different sets of treatment for them. So, in today's lecture, we will talk about equations of state, and in today's lecture, we will restrict our discussion to gases. We have been discussing many equations, many relations in terms of canonical partition function. And the canonical partition function, which we designated as capital Q, is a function of n number of particles, volume and temperature. So, this canonical partition function, which is a function of volume, temperature, n number of molecules, was connected to various thermodynamic parameters, and one such connection was between pressure and canonical partition function. If you remember, we had derived this equation, pressure is equal to kT times del log Q by del V at constant temperature. We can call this is an equation of state, because what is an equation of state? When we talk about ideal gases or perfect gases, the ideal gas law, ideal gas equation or perfect gas law, that is PV is equal to nRT. This is an equation of state for a perfect gas. So, we can call an equation of state as an equation which connects P, V and T. The simplest case is PV is equal to nRT, but remember that this is only for an ideal gas. Now, you come back to this expression, P is equal to kT del log Q by del V at constant temperature. This is a purely general equation. We did not specify this, that whether it can be used only for ideal gases or it can be used only for non-ideal system. We did not specify that. But let us first apply it to monatomic perfect gas. Monatomic perfect gas. Let us do that and see what happens. What we have, P is equal to kT del log Q del V at constant temperature. Remember that if we are talking about monatomic system, we are only discussing perfect monatomic gas. So, Q, canonical partition function, in terms of molecular partition function, is going to be Q raised to the power n over n factorial. Because the molecules are not distinguishable, therefore, we are going to use the connection of canonical partition function with molecular partition function, which is used for indistinguishable molecules. If Q is Q raised to the power n by n factorial, then log Q is equal to log Q raised to the power n minus log n factorial. Can I write this as n log Q minus n log n minus n, Stirling approximation. Fine. So that means my log q is n log q minus n log n plus n. And let me write this on the next page. Log q is equal to, we have n log q, n log q minus n log n plus n. This is what we derived, that is log q is equal to n log q minus n log n plus n. But we are interested in pressure. Pressure is equal to K T del log q del V at constant temperature. And since we have already an expression for log q, we can take derivative of log q with respect to volume. So when you take the derivative of this with respect to volume, this is the only term which may depend on volume. N log n and this n, these are constant. So derivative of these two quantities with respect to volume is going to be 0. Okay. That means the pressure is equal to Kt. Then we need to take derivative of this, which is n by q into del q del V at constant temperature. Since we are talking about only monatomic perfect gas, so Q is equal to Qt is equal to V upon lambda cube, where lambda is equal to H over 2 pi m Kt. Okay, so Qt is equal to then 2 pi m Kt raised to the power 3 by 2 into volume by h cube, V upon lambda cube. So let us now put pressure is equal to Kt n upon q. I am going to write Qt, which is 2 pi m Kt raised to the power 3 by 2 into V, and here I have h cube. This is n by q, then multiplied by del q by del V at constant temperature. I need to take the derivative of this with respect to volume at constant temperature. Constant temperature means entire this factor becomes constant. So let us write down. This becomes 2 pi m Kt over h cube, then del V by del V is 1. Of course, this is raised to the power 3 by 2. This and this cancel, h cube and h cube cancel, and then if I rearrange, I get PV is equal to n Kt is n times Na, that is number of molecule is number of moles times Avogadro constant into K into T. K times Na is R, is PV is equal to nRT. This gives me PV is equal to nRT because K times Na is equal to R. Now I can consume n, I can take n on the other side, and V by n I can write molar volume. So I have PVm is equal to RT. This is the equation of state. We were saying that this is equation of state. by using that, first restricting to ideal gases, we have shown PV is equal to RT or PV is equal to nRT. This is an equation which we have been using for a long time and we called it as equation of state. But this is applicable to ideal system, ideal gases. The gases may or may not be ideal. First of all, we should remember what is the definition of an ideal gas. How do you differentiate between real gases or an ideal gas? Right? Sometimes real gas you call as non-ideal gas. What is the difference between them? When I say ideal gas, that means no intermolecular interactions between them, irrespective of the distance. When I say non-ideal gas or deviation from ideality, that means the attractive or repulsive interactions come into play when you vary their distance from very far to very close. And if you remember, at some point we defined pi t is equal to del u del v at constant temperature. This is equal to 0 for ideal gases. And this is not equal to 0. I repeat, this is not equal to 0 for non-ideal gases. Okay? So, if we were to address the difference between real gases and ideal gases, there can be several points of differences. For example, one we talked about pi t. Pi t is equal to 0 for ideal gas, pi t is not equal to 0 for non-ideal gas. Why? Because sometimes the gas molecules, when you mix two gases, and if these two gases are non-ideal, then they will interact with each other. So, interaction energy can also contribute to non-ideality. There is existence of non-zero Joule-Thomson coefficient. There can be difference in transport properties. I repeat, there is difference in transport properties and there can be existence of non-zero Joule-Thomson coefficient. So, therefore, how to address the deviation from ideality in gases? Looking back at what you study in class 11 or class 12, Van der Waals equation of state, in which A and B were introduced, which reflected upon the attractive and repulsive parts of the interactions. Here we will talk about the virial equation of state and we will talk about virial coefficients. PVM upon RT, which you remember was also called as compression factor. But here we are not going to talk in terms of compression factor. Here we are going to talk in terms of virial coefficients. Let us represent PVM by RT is equal to 1 plus B by Vm plus C by Vm square plus so on so on. If B, C, all these numbers or all these coefficients are 0, then you simply have PVM is equal to RT, then it becomes an ideal gas. In this form of the equation, B is called second virial coefficient, C is called third virial coefficient and so on. Obviously, these virial coefficients are going to depend upon temperature. Why? Because when the temperature is increased, the intermolecular interactions between the gas molecules will also be affected. Therefore, these virial coefficients B, C, etc., these virial coefficients vary with temperature. So, our purpose is to somehow connect these virial coefficients with canonical partition function. Then we can move towards bringing in non-ideality into our discussion. Let us do that. But before doing that, let us recall some of our earlier learnings. One of the earlier learning was that the total kinetic energy of a gas of molecules is sum of the kinetic energies of individual molecules even when interactions are present. When we only talk about kinetic energy, I am not talking about potential. The total kinetic energy of a gas of molecules is sum of the kinetic energies of individual molecules even when the interactions are present. That means now in a real gas, the canonical partition function must factorize into a part which is arising from kinetic energy, that is going to be same as that for the perfect gas, and another factor called configurational integral. That is what is commented here. Okay, thus in a real gas, the canonical partition function factorizes into a part arising from the kinetic energy which is the same as that of perfect gas and a factor called configurational integral. This we will call as Z. Obviously, this Z, which is configurational integral, it is going to depend upon intermolecular potentials. Now, this canonical partition function is represented as Z by lambda raised to the power 3n. For perfect gas, you have already studied that this is equal to V raised to the power n by n factorial, where V is the volume of the container, and this is according to this definition because Q is then partition function for a collection of non-interacting particle. That means if Z is equal to V raised to the power n by n factorial, we are talking about perfect gas. We are talking about non-interacting particles. Alright, let us move ahead. From the ideal gases, now let us move towards a real gas. When we talk about real gas, we are talking about intermolecular interactions. That means we have to now, in addition to the kinetic energy, we have to bring in the potential energy. And let us represent potential energy as Vn. This potential energy of interaction is related to the configurational part Z, which was, if you go back, this configurational integral Z for ideal gas was V raised to the power n by n factorial, but for a non-ideal gas, this will be 1 over n factorial integration exponential minus beta Vn dr1, dr2, etc. drn. What are these dr, dr1, dr2, dr? This integration of each one is equal to volume. We are not getting into the derivation of these, you have learnt at some point, but we need to know, in order to evaluate this, we need to know the potential. Though we are not getting into the derivation of this, but we can go reverse, that we can show that this converts into the configurational integral for a perfect gas when you ignore the potential energy. And when do you ignore the potential energy? When the interaction between all the particles is switched off to 0, perfect gas. If you put Vn equal to 0, then exponential 0 is 1. In that case, Z is equal to 1 by n factorial, dr1, dr2, etc. And since each one is volume, then this is V raised to the power n by n factorial, and this is what the configurational integral was defined for an ideal gas. Distinguish between this Vn and this Vn. This is the potential energy and this is the volume of the container. Okay. Now, let us consider only pairs of particles. You can consider 2 particle interaction, you can consider 3, 4, 5, you can keep on increasing, and that will bring in more complexity. But for a simple example, let us consider the interaction between only pairs of particles. So we will write Z2. This is equal to 1 by 2 factorial exponential minus V2 by kT dr1 dr2. And using this, again we are not going into derivation, the second virial coefficient turns out to be B is equal to minus Na by 2V into F, integration of F dr1, dr2, where this F is expressed in terms of potential, minus V2 by kT minus 1. Na is Avogadro constant. So that means if we know the potential, somehow if we know the potential, then we can have B. This F is called Mayer F function. Remember, this is called Mayer F function. Obviously, when you put V2 equal to 0, then exponential 0 becomes 1. 1 minus 1 becomes 0. And if F becomes 0, that means then in that case B also becomes 0. Right? It says it goes to 0 when two particles are so far apart that V2 equal to 0. So if you are talking about the particles which are very far apart, that there is no interaction between them, then the interaction potential energy is 0. V2 is equal to 0. If V2 is equal to 0, then your virial coefficient is also equal to 0. So this explains that when the particles are very far apart, in that case this F value turns out to be 0, and then you can see what happens to the value of B. Now consider that the intermolecular interaction depends only on the separation of the particles, but not on their relative orientation. Please listen carefully. When the intermolecular interaction depends only on the separation of the particles, separation let us represent by R, but not on their relative orientation. We can take an example, for example, in closed shell atoms and tetrahedral or octahedral molecules. In that case, this equation B is equal to minus Na over 2V into F dr1 dr2, where F is this is the same equation that we discussed earlier. This B transforms to minus 2 pi Na 0 to infinity Fr square dr, and this can be evaluated numerically provided we have this Mayer F function which is dependent upon the potential. You can have, depending upon the potential energy, you can calculate, you can evaluate the second virial coefficient numerically. All right. Now, what we have is the expression for B, which now we have derived for when the potential energy only depends upon their separation. So consider hard sphere potential. This hard sphere potential is infinite when the separation of the two molecules R is less than a certain value. Remember the potential energy curve. It will go take a dip and then again it will increase. So we are using the same principle, that when the separation of the two molecules, which is represented by R, is less than or equal to a certain value, right, then the potential becomes infinite. For example, you see here, if the potential energy for a certain values are less than sigma, it becomes infinite. Then you put V2 equal to infinite over here, exponential minus infinite 0, 0 minus 1 is minus 1, in that case F is equal to minus 1. So if F is equal to minus 1, then B becomes, you can connect this over here, B becomes 2 pi Na R square dr from 0 to sigma. Sigma is that minimum value, which turns out to be 2 by 3 pi Na times sigma cube. This is the case when the separation of the two molecules R is less than or equal to certain value. On the contrary, if R is higher than sigma, let us say the molecule, they are far apart, then you can take potential energy to be 0. In that case, F also turns out to be 0. So what we have derived is that the second virial coefficient B is equal to 2 pi Na integration 0 to sigma R square dr, which takes up this form 2 by 3 pi Na times sigma cube. You remember that van der Waals equation of state. P is equal to RT over Vm minus B minus A over Vm square, where A took care of the attractive parts of the interaction and B took care of the repulsive part of the interaction. So here also the hard sphere repulsive part of the intermolecular potential B, that contributes to B in exactly in the same way. But these are some of the extreme cases which we derived. The question is, can we find a potential, the actual potential? Here we need to have the value of V2 to evaluate the exact B, C or any other virial coefficient. So can a potential be found which, when the virial coefficients are evaluated, provides the full van der Waals equation of state? The answer is yes, such a potential can be found. We have talked about second virial coefficient. Similarly, the extension of the discussion can be made to other virial coefficients, and you will also require to have knowledge of how to find a potential which actually represents those intermolecular interactions, but that is beyond the scope of the current discussion. What I have discussed in this lecture is that the gases which do not follow ideality, which are not ideal, which are not perfect, will show non-ideal behavior and will undergo intermolecular interactions. How to incorporate those intermolecular interactions, how it is reflected into virial coefficients, that's what we discussed in this lecture. I hope it was useful and it will form a basis for your higher learning. Thank you very much.